homework number 1 and phase 1 of the project. Just I talk about that one quickly, and after that I'm going to go over the three-phase sinusoidal PW for the three-phase inverter. Before going there, today I was supposed to stay after the class. To be honest with you, I'm not feeling good at all. No, I am really sick. Just getting a little bit better right now. We're not gonna have an extra class today. We'll finish it around 6:18, 6:20, something like that. And next week Tuesday I'm not here. And when I come back from Chicago, we'll go over the makeup class. We'll make it. Yeah, I have to have a makeup class for the next Tuesday. I'm not here.
So there's no class tonight?
No, next Tuesday no class.
Oh, okay.
No, next Tuesday there is no class. I'm not here. You can come here if you want. You can come here.
No.
Watch the board, but I'm not gonna be here. So homework number 1 is clear. You go over it and you see that one. But the phase 1 of the project. See, basically the three-phase inverter. The three-phase inverter. The sheet I gave you. You're gonna simulate that one for different loads. But how to switch the inverter? If you look at this sheet, I gave you this one. The 6 first waveform, right? They are there for I don't know what it is. S1, S2, 3, 4, 5, 6. I'll suggest you to do it this way because it's going to be very easy to modify this version of your simulation to the sine PWM. Say you have a 6 switches. You have a 6 switches, right? One, 3, 5, and I don't know what's the number for the rest. They're complementary of the top one, right? So if you look at this sheet, you can see this one. If you look at it, it's like this. It's the 180, right? And 0 for 180, and again 180 for the one for the next 180, right? That's what is in this sheet. You can see. This is number 1. Number 3 is basically the same thing, shifted 120 degree, right? So if you look at here, this one is going to be like this also, right? This is another 180 degrees, right? Shift this one 120, right? If you shift this one 120, it's going to be like this. This is 120, right? And this is a 180, and this is 180, and whoa. Now, for the number 5, which is the phase C, again, you shift this one another 120, right? If you shift this one another 120, it's going to be like this. So basically, this is 180, 60. I think the next one is going to start from here. You have a 180, should be 180 off, and again here like this. Something like this, right? Now I want to tell you, this is what you need to send to your switches, right? The gate of your switches, right? Because I want to tell you how to build this signal. To build this signal, you are going to use a PSIM, right? PSIM has you can go select a 3-phase source. This is a 3-phase source, right? Just set the phase angle. Have you worked with PSIM, guys? You haven't worked with PSIM? This is the software you're going to use this year, this quarter. Last quarter we had PSIM also, right? For simulation and those kind of things. You could use a SimPlorer or PSIM. PSIM is much easier, right? More user-friendly for this kind of simulation. It's going to help people a lot. It's going to be much less pain compared to SimPlorer. But SimPlorer is much better. Much better, I'm saying, is stronger. It has more tools to use. But for this kind of things, PSIM is more than enough. You have everything you need. But by the way, you go select the 3-phase circuit. This one, do it this way. Put comparator here, comparator here, comparator here, plus, plus, plus. Compare all these one to ground. What is going to happen? What comparator does? If this signal is more than how much? 0, it's going to be high. If it's less than 0, it's going to be low or 0, right? So if you look at the sine waveform, it's like this, right? This is sine waveform, right? This is 180 degree, right? This is 180. So for the first 180 degree, this is phase A. Keep in mind, this is phase A, right? So for this part, it's going to be 1. For this part, it's going to be 0. If you look at here, basically this signal is going to be like this. 180. Right? This one is going to go to 1. Number 1. And the knot of this one is going to go to number what? I don't know, because this one's 4, I think, right? It's going to go to number 4, right? Here, we said, what should we have here? Shift this 180 degree, right? Phase B, automatically in the three-phase system, is 120 degree shifted, right? Basically, if you look at phase B, it's going to be like this. This is A, this is B, right? If you compare this one to 0, during this time, it's going to be high. During this time, it's going to be 0. It's going to create the second signal for you, right? And the same thing here. This one is going to go to 3, and the knot is going to go to 6. And the phase C is going to go to 5, and the knot is going to go to. The reason I'm saying do it this way, we're going to go over sine PW for 3 phase. Just right after here, I explained this one. The next phase of this project, the first phase you do the 6-step inverter. This is what we explained about. The next phase I want you to do it with the sine PWM. Sine PWM, you have to have a carrier waveform and triangular waveform, right? We explained how sine PWM. So you can easily use the same program you build. Instead of putting this one 0 here, you're going to put the sawtooth or a waveform like this, right? Just replacing this one, you're going to have sine PWM. I'll show you. I have the simulation. I'll show you later. So my point is, so it will be a very, very short transition going from 6-step to sine PWM, open loop, But if you want to generate all this signal, also you can. You can make a signal generator generate these things for you. You know what I'm saying? Like a function generator. You have function generator in the lab. You can go program for this guy. You can do it that way also. But this is the easiest way to go over it if you guys, you want to do it. Just do it this way, and the rest is there. The due date for homework number 1 is next Thursday when I'm coming back. For the phase 1, let's give it until the Tuesday after next Thursday, The Tuesday after next Thursday. I don't know what date it's going to be. The Tuesday after next Thursday.
It's
yes.
the 28th.
Because this phase is simple. It shouldn't take that much time. The whole simulation maybe should take let's say this is the first simulation you are doing, getting familiar with PCing, you should be able to finish it in five hours maximum. I'm saying in 5 hours top. If you know the PCing, already used the PCing, should be top 2 hours. 2 hours, I'm saying, But the writing report is going to take a little bit time. All those cases I mentioned, for example, one case I said, ABN, the inverter would be in the same phase with the grid. How we can do that? Can somebody tell me? See, this is what we have. Inductor, and this one is going to go, and there is a resistor, I think, here. And this one is going to go connect to the grid, right? The first one I said VABN, ABCN. ABCN is from the inverter. Be in the same phase with this one. What does it mean first? What was the VAN here? Remember? It was like this. Right? You can look at the sheet I gave you last week or last week. When we say in the same thing, this is the output of the inverter, right? When we say grid voltage should be like this. This is in the same phase. Grid is the same phase with this voltage, right? How you can do this one? Huh? No, this is simulation. I'm saying how to simulation you can do. Well, how did I say to create this one here? This one? I said do this one, right? Select this one to be in the same phase with the grid, all right? So this one is part of your control system. It's going to be here, right? But here you have another three-phase system, right? Make sure these two they match each other. They match each other, not amplitude-wise, phase-wise. You know what I'm saying? Because here is going to be, I don't know, 208, whatever voltage I give you. If you look at it here, on the power side, it's going to be like this. For example, 208. On the control side, you don't go more than 1, right? So it's going to be like this. You know what I'm saying? But in the same phase, right? If you put this one in the same phase with this one, this one is going to be exactly the same thing. When I say go, I don't know, 90 degree leading or lagging, just add plus 90 degree or minus 90, you're going to shift it in 90 degree. You cannot shift this one. See, be careful what you are doing. In simulation you can, but in reality you cannot shift the grid, right? Grid is saying that I cannot do anything about the grid. But I can shift my control signal. This is what I have in my microcontroller, right? Or my DSP. I can shift it this way or that way. It's easy to do that one, you know. My point is, yes, in simulation you can go shift the grid, but don't shift the grid, you know, because in reality it's not possible to do that one. So you shift your control signal and say, okay, instead of having this one, I'm going to have this one. Now, this is a 90 degree shifted, right? Lead or lag, you can put it that way, right? Okay.
Is that how you would normally implement your control signal, microcontrol?
Exactly, that's the way we do it, you know. Usually, we are not going to go over PLL, but usually you have a PLL phase lock loop. They call it phase lock loop. It's going to go find the phase of the grid. So now, I know where is my grid. If I want to be inductor, I can shift it that way. If I want to be capacitor, I can shift it that way. If I want to be resistive, I can do it like the one I said, we keep it in the same phase. You know what I'm saying? So grid, I cannot move it. Grid is fixed. I need to go find out what is grid. And now respect to that one, if I know where is the zero of grid, I can either go leading or I can go lagging, right? So that's exactly what we do in the real microcontroller system. Yeah. There is a very high possibility, very high possibility, a power system course for those when they want to go through the power depths. I know for some of you this is the third course in the power. I think there is very high possibility a course power system analysis will be offered next year, either fall or winter, you know, either fall or winter. And for those when they want to take the depth, they can take that course out there and they could have a power depth. Now, any question here? Okay, let's go to the sign PW. Let's go to this concept. this one, right? And we talked about this one, how much is going to be VAN. How much was the VAN? We went over this one. For the single phase sine PWM, we talked about that, right? It's going to be VDC over 2 times 1 plus, I'll call it here V con A over VTR, am I right? I put it this way. So, if V con A VM, okay, more your sine or cosine, let's go sine. Sine theta, right? So, VAN is going to be VDC over 2, 1 plus VM over VTRI cap, right, sine theta, right? We call this one MA, right? Modulation index, the VM over VTRI cap, we call it MA, right? So basically VAN was VDC over 2 times 1 plus MA sine theta. So keep this one. If we have phase B, how about VB? I don't have them here. Now if I have this one, A, B, C, N, right? How about the VBN? How much is the VBN?
VDD.
VDC over 2, right? VDC over 2, 1 plus MA sine of what? Theta minus 120, right? And VBECN is going to be theta minus what? 240, or we can say plus 120, right? Right? So it's gonna be this. So this is for three-phase system sine PW. Basically, you have, let's call this one DA, let's call this one DB, let's call this one DC, right? So you have a DA is MA sine theta, DB is MA sine theta minus 120, and DC is MA sine theta plus 120. These are your modulation signals, right? Now, let's advance it a little bit. Let's say we have a load here. N. I'm going to call this one N. Based on the sheet I give you, this sheet, you have it here. So, VAN, this is my output voltage, VAN. First of all, let us start with the VAB. VAB, we said the VAB or VBC or VCA, they are not going to have a third harmonics. Why?
Equals to 0.
Equal to what?
It becomes like sine of
Because we have 1 point.
Because it's going to be, for example, VAN, right? It's going to be VAN minus VBN, right? Is the VAB, correct? And we said VAN is going to look like what? Here, if you look at it, VAN is going to be like this. VDC 0 VDC, right? You have all this, and you don't have to redraw it again. You know, that was the VDC like this, right? That was the VAM. Now, we said this waveform, we know it has a third harmonics, right? And that's a DC value, right? So we said, but the thing was, this one has the same DC value. When you subtract them from each other, the DC is gone. The third harmonics, this one is going to be sine of 3 omega t. This guy also is going to be sine of 3 omega t, right? So 3 omega t minus 3 omega t, they're going to cancel each other, right? So there is no third harmonics. If you look at the VAN, for example, in the note I gave you, is a 2/3 of VAN, right, minus 1/3 of VBN plus VCN, right? Again, if you look at here, these two, all these three, VAN, VBN, VCN, they have the same DC value, right? But look at here, in here is it 2 times of DC value of VAN minus 1 time of DC value of VBN and 1 times of DC value of VCN, right? All of them, they have the same DC value. How much is the DC value for all of them? VDC over 2. See, this is the VAN, right? This is the VAN. This is the VDC, 180, 360. How much is the average of this one? VDC over 2, right? So, average of this one is VDC over 2, average of this one VDC over 2, average of this one VDC over 2, right? So right now, at first I want to talk about the VDC. So VDC over 2 plus VDC over 2, this one has an average value of VDC, right? Divided by 3. So VDC over 2 VDC over, sorry, it's going to be VDC over 3, right? This one was the VDC over 2, this one is the VDC over 2, right? It's going to be VDC over 3. How much is this one?
1/2 VDC.
This is a VDC over 2, right? Let's cancel these two with this 2. It's going to be VDC over 3, right? VDC over 3 minus VDC over 3. So there is no DC component in the output. That one is clear, you know that, you know. If you look at the VAN was like this, right? There is no DC value, right? So how about third harmonic? So the third harmonic for this one and this one, they're the same. Why? 3 times 120 or 3 times minus 120, 360 or minus 360 is gone, right? There's a sine 3 omega t, sine 3 omega t. There's a 2 sine 3 omega t, right? This one has a sine omega t, right? And there's a 2 here. 2 sine omega t minus 2 sine omega t, right? So there is no third harmonics here too, right? So my point is, the line voltage doesn't have a third harmonics, doesn't have a DC value, doesn't have a 9 harmonics, doesn't have a 15 harmonics, right? This one, the same thing. We call this one phase voltage, VAN. It doesn't have a DC value, right? It doesn't have a third, 9, 15, 21, and all those ones, they're gone, okay? Just I want to remind this one. Question?
I was just asking if the VA to the little n, that's line voltage?
No, VA to the N is this one, see? VAV is a line voltage, VAN is a phase voltage. This is this phase, look at here.
Okay.
We call it phase voltage, right? Now, I want to go, I have VAN, I have VB and VCN, which is sine PWM. I'm going to go find my VAB and VAN. Should be easy, right? So how much is the VAB? Yep, VAN minus VBN. Exactly. VAB let's put it here. So this part is going to be gone, right? Both of them, they have MA, right? It's going to be half of or VBC over Q this one here. I'm gonna simplify this one. How about the VAN? Again, I'm gonna go back to this sheet, to this cheat sheet. It's gonna be 2/3 VAN minus 1/3 VBN plus VCN, right? So if you want to find this value, you will put this one, right? Basically, this VDC over 2, they're gonna go away. Is gonna be 2/3 of sine theta, right? This is this part. I wrote this part. Because VDC over 2, they're going to cancel each other, right? It's going to be this one. And this is the fundamental harmonics. You know, we're talking about the first harmonic, not the rest. Minus 1/3 of the second one is going to have a VDC over 2 so MA sine theta minus 120, right? Plus right? Let's start with this one, it's simpler, you know. If I add, look at here, I'm going to add 1/3 of VDC over 2 MA sine theta, and I'm going to subtract 1 minus VDC over 2 MA sine theta, right? I add this and I subtract it, right? No, I think I'm doing, hold on, let's see. 1/3. Correct. Now, look at here. I'm going to take this one inside this brackets, right? So 1/3 should stay out, right? Is here. Minus is going to stay out. What's going to be inside the bracket? It's going to be this plus this plus this. Am I right or not? Correct or not?
Yes.
How much is that?
0.
Why?
They're all out.
Yeah, this is a three-phase system. You look at it. Sine theta, theta minus 120, theta plus 120, all of them, they have the same magnitude. So that one is 0, right? Now look at here. I have one still here. I have a 2/3 and 1/3. It's going to be how much? Is that VDC over 2? And the phase A voltage. Good or not? Do you like it or not? See how simple it is? The phase voltage here is going to be half of VDC times MA, and the sine theta is the phase of the voltage. It's the same sinusoidal. I'm talking about the first harmonic. We have more harmonics, you know, but the one I'm focusing on is the first harmonic. That's important for us, right? How about, so I'm going to write it here. So here we proved it, VAN is going to be half of VDC MA sine theta. Can somebody tell me how much is going to be VAN? Right? Right? Is it clear here what I did?
Can you explain how you split up the first term again?
How I did what?
How you split up the first term?
No, I didn't split up that anything here. I said, just I'm gonna add this one, I'm gonna subtract this one, same thing I added,
Oh.
right? Maybe I said something. Just I'm adding this one and subtracting it. If you add this one together, it's going to 3 over 3 this point, right? If you take this one inside this one, this bracket is going to be 0, right? Yeah.
So basically you're saying VA small n equal to VA capital N.
Huh? I'm
The
saying
phase
what?
voltage is equal to the line voltage in the phase, the expression.
No, it's not equal to line voltage.
When you look at expression over here.
Hold on, let me calculate this one, you know. You know, next step we have to make sure the energy conversion is a prerequisite for power electronics. Well, let's look at again. I want to see what is this. The MA is fixed, right? So it's gonna be, if you go with a phasor, this is sine theta, right? This is sine theta minus 120, right? So I'm gonna select, I have a sine theta. This one is going to be 1 with the angle of 0. I select this one as my reference. How about this one? Sine theta minus 120. Right? Just I want to make it simple to calculate it quickly. You can do all the math calculation, but for those one they have energy conversion, it's a piece of cake. They don't have to go through this one, but for those one they didn't have it. So here I have this one minus this one, right? Let's put it here. This is the first one, right? 1 with a 0. And this is the circle. Right? So which one is this one? This one is this, right? This is a 1 with minus 120, right? Now, I want this one minus this one. So it's going to be this one plus minus this one, right? What is minus this one? Right? This is a minus, I agree, right? So now this one plus this. I learned the word actually, you know, it's a parallelogram. I believe I practice it a lot, you know, to get, you know, parallelogram, you know. I'm not sure still I pronounce it well, but I think it's close enough. This is the result, right? Minus 1 with 120. So how much is this one? I want somebody to answer this one very quick. How much is this one?
Root 3.
Not you. No one they had energy conversion, they should say it quickly.
No one had it?
Those when they had energy conversion, they should say this should be a piece of cake for them. Root 3. This one is the root 3. This is 1, this is the phase, this is the line, right? Square root of 3 times this one, right? And this angle is 30 degree, right? So to make it, you know, final, so basically this one now is a square root of 3 with an angle of how much? 30. So this one is going to translate to what? A square root of 3 sine theta plus 30. Right? I will back it up in here. You can go do your math if you want, but sine theta minus, I'm going to put this MA here. I'm going to put the MA here. Sine theta minus tan theta minus 120. This one is going to be the square root of 3 sine theta plus 30, right? It is here. It's going to be right? If you want to calculate B, how much is B? VBC. How much is the VBC?
Similar but shift
So it's going to take plus 160, right? BCA minus 90, right? Okay, we discussed all this in energy conversion, you know, but just here is 3 bases. Yeah.
Just want to clarify on the terminology. So VAB is the line voltage.
Yes.
VAN is the phase voltage.
Phase voltage.
And what about VA capital N?
Oh, that one is respect to this one.
Yes. Is that
You can use the VAB or VAN or anything else, and do those things to calculate VA small n, you know. Now, let's compare this to this. What is it different? This is line voltage, right? That one is the phase voltage. Line voltage is the square root of 3 times phase voltage, right? That one is the half a VDC, this is the square root of 3 times half a VDC, right? And line voltage is what? 30 degree ahead of phases. So basically this is exactly like we have in a three-phase system. Now we're going to go through another thing, you know. And this is all we are doing. This is for first harmonic we are talking about, right? So let's take this one now. Let's take this one. We line to line first harmonic. How much is it? Maximum value, right? Max, let's put the maximum. How much is it? We line to line root 3 VDC over 2 mm, right? This is the maximum line to line voltage for the first harmonic, right? The reason I'm just emphasizing on the first harmonic, when you are going to design this inverter, you focus on the first harmonic. You design your system based on first harmonic, but later on you're going to go back, consider the effect of the rest of harmonic, and say, okay, how bad is going to make it, you know what I'm saying? But you design for power delivery, for everything, you're going to design based on the first harmonic, right? Now, how much is the V line to line 1 RMS? That one divided by root 2, right? Can somebody calculate this number for me? .22 and divided by 2. I know the answer. It's going to be 6.612.
Yeah.
But double check it. You know?
0.61.
Yeah. MA. Okay, this equation, if you are going to be a power electronics engineer, you should memorize it for your life. So V line to line 1 RMS is 0.612 MA. You know, this one makes you really look smart. You know, when you do this calculation quickly based on this one, people they say, how did you calculate it? You know, wow. You don't know that much. You just one equation. Believe me, it has happened to me. You know, you go to talk to these people. They in microgrid, UCSD. They have the battery, those kind of things. And I asked them, how much battery did you put here? And they start to look at each other. How much is it? Just I do. Okay, what grid you are connected? Is it 480? So if we get 480, right? Just keep MA 0.95 because you don't want to go more than 1, right? More than 1 is going to be non-linear, right? So over modulation. Just calculate this one. I think you're going to end up 800 something like that. Calculate this one. 480 divided by 0.612 times 0.95. Somebody calculate this one. I think it's going to be about 800 volts, something like that.
It's 825.
825. So you need this much battery to connect to the 480 system. When you have this inverter here, if you have a load 480 or you have a motor or you have a grid here, you need to have how much battery here? 825 volts. Go check does anybody have the copy of the project I gave you? Did anybody create it? Because I want to see what numbers did I give you. This is the minimum. Be careful. This is the minimum. It could be more. Why I'm saying this is the minimum?
As
As the battery runs down, like
No. Yes, sir. But I'm saying if it's less than this, what's going to happen? If it's 750 volts. Worse than that. Hmm? No, disaster. If you put a 750 here, the maximum voltage you're going to get is how much? Less than 480. Your inverter cannot be connected to that voltage. You know? So either your MA has to go up to compensate for that, right? Let's make this one 700. Still you want to get 480. MA should be 1.2, 1.3, something like that. What does it mean?
Over modulation.
Over the modulation, right? And we don't want to do that for the control purposes. So that's the reason I'm saying at least 825. And the 5% I put here, can somebody tell me why I didn't use 1?
That's the worst case.
Margin of error.
So what's the worst case?
Maybe 5%, yeah, output, pH,
No, not THC, not THC. Look at here. In the grid type, it's going to be like this. In the grid type, you have this inverter, just I put the box here. 3 lines coming out, you have the inductor, look at the project you have, and you have the grid here, right? Right? Here is 480.
You can have moment velocity.
Look at some block, voltage drop here, right? And if you look at it, maybe it's 5% more. So just put 480. Right? Because if you look at here, the current is going this way. You got this voltage plus this voltage, right? So here is going to be a little bit more, right? Right or not?
Correct.
Another thing, usually they tell you, they say the grid could be plus 10% minus 5%. Now what you should do?
max.
So 480 plus 10% is a 48, let's say 50, is going to be 530. You should select 530 times 105 and put it here, right, to size your value. But there's some good news. There is another way, they call it space vector modulation. We'll talk about that one. Whatever you calculate for sine PWM, you can divide it by 1, you can reduce it 15%. Divide it by 115, you'll get to that number. How we get to that number? So basically, 750 volt bus is enough for a 480. If you use a space vector PWM, which you already simulate now, don't worry about that. You're going to simulate that one. You simulate it with sine PWM and you simulate it with a space vector PWM. Okay, so what we did here, we went through the sine PWM for 3-phase system. We calculated the first component of the line-to-line voltage is this much, or we can go here. If you want to calculate this one also, is going to be how much is the VAN? The phase RMS is going to be this, right? This is the max. I don't know how much is this number, but you can calculate. This is the RMS of the phase voltage, right? That's another one if you want. Now we are gonna look at the MA, linear modulation, over modulation, and 6-step operation. If we look at that one, it's gonna be like this. If we look at that one, it's regular. How much is this one? If MA is 1, how much is this one?
0.612.
Right? And after that, it's going to go like this. Right? How much is this one? Go back to look at this one. Right? If you go back look at this one, VLLH, go back look at this one, VLLH or VLL1, I put it here, is 0.78 VDC, right? I don't know what's this this number. I'm gonna check the net Mohan books is gonna give us, I don't know, it's gonna be 1.4, something like that. We'll check it to see how much it is. Here is the linear modulation, right? What is this? Over modulation. And here, what is this? For the single wave, for the single phase, we call it what? A square wave operation, right? Because the output is a square wave, right? Here we call it 6-step operation. Okay, let's look at this slide. This is the three-phase inverter. This is what we showed here. We posted this slide. This is the first slide. Let's go up. Let me see what is that slide. Here it's talking about the power factor and operation and the system. It can be leading, lagging, unity, all those kinds of things. This is this. For a single phase system, this is how we did that. We did prove that equation, right? This is what we went through to prove that equation. This is for the unipolar, that was the bipolar harmonic. This is for the single phase inverter, and this is the square wave, half bridge, single phase full bridge. This is for bipolar. This is spectra for the unipolar. This is a harmonic combination. I'm going to talk about this one after that. Single phase inverter. This is the P and Q. We talked about it. Push pull forget it. Three-phase inverter. Yeah. This is the, you can see it here. This is the V control A, V control B, V control C. This is the three I selected, you know. Yeah.
Is this chapter 8 from the Mohan book?
Yeah. This is all. This is slide is uploaded already. You have it in your. I got the permission from you. I can upload it. You know. You can use it. There's no problem with the copyright and problems. The book I cannot post it, but I can upload the slide. You know. So over there, if you look at it, there are three control waveforms: A, B, and C. This is a phase A control, phase B, and phase C. There is this triangular waveform here. This is exaggerated. We are switching very slowly, but because it wants to show you what is happening, it went with a very low. Because I'm going to show you the simulation. When we plug these two on top of each other, you don't see the V control at all, because that one is the frequency of the sine with the carrier waveform is much, bigger than the sine waveform. It's blocked over. You're not going to see it. But here you can see when, as we explained before, if V control A is more than triangular, VAN is positive. If it's less than that, it's 0. The same thing we're doing. And here he built the VAN. VAB, sorry. Here he built the VAB here. VAN minus VAB. See, it looks like this. This is the harmonic spectrum for this one. Look at it. Very similar with what we had for the single phase bipolar, but this one doesn't have a third harmonic. So keep in mind, third, nine, those kind of things. Look at here, this is the first. This is the MF plus minus 2, MF plus minus 4. Remember exactly what we had for that one. Here is 2MF, there is nothing, but 2MF plus minus 1, 2MF plus minus 3, 2MF plus minus 5, exactly like the table we had for that one. And the next one here. And look at here, even this MF is not that big. Remember the one in the single phase was pretty big. It was the same magnitude as this one, right? But this one is much bigger than that. I think the table is the next page. Yeah. This is the harmonics you're going to see. This is the MA. MA. How much is the output voltage for MA? This number, right? This is normalized divided by VDC, right? If MA is 1, how much we have? 0.62. 0.62. But this one is only 1/3 of it. Look at here. This is a, plus minus 4. And you go to the 2MF plus minus 5. 2MF plus minus 5. 2MF. There is no 3. No, there is the 3 there. 2MF plus minus 7. Those ones are 0. You didn't put it here anymore. 3MF. So this is the harmonic spectrum you are going to see for this 3-phase inverter in the output voltage line. This is for the line voltage. Remember. Any question here? Actually, I should have talked about the harmonic elimination before we signed the algorithm. But now, if you don't have any question, we're going to go to harmonic elimination. We go through the harmonic elimination, and we finished. I'll go through some simulations with the sine PWM, and we finish today's course now. No question here? Is it easy, guys, or other way? No, this is the one I forgot. See, 0.62, this is the point I put it here on the board. Looks like it's not going to happen at 3.24. It's going to be like a, we call it a square wave, but this is 6-step operation. Not the yes, that's this, they call it 6-step operation, not a square wave. But he calls it a square wave. That's not big deal.
What does the output look like under square wave operation for 6-step?
So this is 6-step. Okay, here. This is the VAB. It's going to look like this. It's going to look like this. But for the sine PWM, does it happen? See, this is the sine PWM VAM. Okay, here. It's going to look like. When you simulate it, look at this waveform. This is VAN, phase voltage. Phase voltage. This is much closer to sine waveform. See, this is a 6-step. This is a sine PWM. This is a current equal. Look at these two. This is much better than this. This one is not a very high frequency. Maybe here you can listen. But if you go to MF 200, you will see the effect very well. I'm saying this is much better than this one. So you want to reduce the current equal to 0. This is the DC side. Oh, this is the harmonic elimination I'm going to talk about. This is the harmonic elimination I'm going to talk about. This is the last topic for the today class. Let's go over it to see what it is. We talked about the harmonic elimination for the single phase. The same thing is going to be here, but you don't have to be worried about third harmonics, right? The third harmonics is going to go away by itself. So we're going to be worried about fifth and seventh and the rest. Okay, let's go over the harmonic calculation. Let's show you simulation because I'm going to use my laptop. Let's look at that. See, I have these notes, but we are doing lots of mistakes, you know. Oh, PC, sorry. I'm doing PC. But it has lots of mistakes. I can upload them, but there are lots of mistakes, you know. Sign PWM, okay, let's see. Do I have the 6 steps first here? 6 step is here, look at here. We talked about that. See here what I did? This is the 3-phase. Let me click on this one. See, here is a 0. Because this is 0, really it doesn't matter what's the magnitude of this one. Whatever you put, I think I just pick something here. Let me see how much I put here. Yeah, this is a 400 AC. Usually you don't put that one. You just simulate it quickly. You put a 1 volt, something like that. But for this one, really doesn't matter. Why? Because you're comparing it to 0. As soon as more than 0 is 1, less than 0 is 0, right? But I have a 3-phase here. Look at the phase. Initial angle phase for phase A is 90 degrees. Frequency is 60 Hz. Make sure the frequency is the same here and there. Here and here, make sure you select the same frequency, these two. Now, as I said, because this is comparing to 0, it doesn't matter how much you are putting here. But let's look at the output voltage here.
Why did you start phase A at 90 and not 0?
We can start at 0, but I don't, maybe over there I started 90, I don't know, let me see. Let me see how much here. This is maybe another, how much is that? That one is 0. This is one of the cases I said shift it 90 degrees. So let's look at it. And here, see this is the good thing with PC. There is a watt meter and var meter. You can measure P and Q. It measures easily for you. Now look at here. Let me put 0 first, you know, as you mentioned. If you are in the same phase, what is going to happen? How much reactive power I have? Let's see, is it correct or not? Let's run this one. How many people they say I do with 0? Why?
Because there's no phase shift.
Huh?
There's no phase shift.
There is phase shift. There is. Okay, it's 0. It's 0. Let's look at it. So first I'm going to look at, I think this is the grid voltage, VAN. I need to go look at it to see. Yes. This is my grid side. That's the VAN is here. This is my VAN. This is A, this point to this node is N. So if you look on this one, this is the VAN. You can see here. The name of this one, yes.
So in the project, when you say V, A, B, C, N, that's just A and B.
Yes, exactly, exactly. And here is my VA inverter. Look at here, N. A inverter. Grid to N is different from inverter to N, right? Because there is an impedance over there, right? Because I'm saying what I'm going to show you. I'm going to show you the voltage of that point, VA of that point respect to the neutral point over there. This is what we calculated in the equation. And you know the VAN already, let me see. And this one is going to be, this one is the W31 is the wattmeter. This one is the VAR31 is the Q meter. Let's look at that. But before going there, actually, I should have done. Do I have a VAB or not? Just here. Okay. VAB inverter. We don't have the VAB. So let me just put the voltmeter here. So I want to measure the VAB, right? This one. And I want to measure the VAN also.
This is a VA big N.
This is, yes, exactly. This is VA big N. Maybe I have to select, I should have selected different letters, you know, we don't go through as much pain. Call them VAN. Let's run it again. Now we're going to plot everything. All the components we talked about. Oh, maybe you want to see here also, right? Yeah, let's call them here. Yeah, let's look at this one for now. Why here is not updated? And so, let me put 3 more here. Don't worry, if you don't have time, I don't go over the modulation, but I want you to see this thing because this is your first simulation. See here, this is phase A. This is the B. This is the C. I'm going to call this one VA gate. I'll call it VAG. Basically, this is number 1. This is a VBG. And this one is the VCG. Now we can see everything. See, these are for current sensor. Look at here. These are current sensor. If you want to look at the current, you can put them here. It's almost done. So, first we are going to go look at VAG, VBG, VCG. VA and VB, VBG, and VCG. Look at here. This is the VA. This is shifted 120 degree here. And look at here, compare this one with this one. Right? This is what I said. Let me zoom in. Let me zoom in here. You can see that. Look at here. This is the A, right? From here to here is 120 degrees. This one is shifted 120 degrees. And look at here, compare this one with this one. And 120 shift. Now let's look at VAB. Or let's look at VAN. VAN is going to look like a VAG. Let's look at VAN. 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 It's going to be exactly like a V. Okay, let me give it up. 2, 3, so you can see VAN is going to exactly look like that. The only difference, what is this? This is VDC. Let's go back to the simulation. Look at, see, that's 700 volt, I believe. I don't know how much I had it, but it is 650 volt. 650 volt is going to be there. Now, the next one we are going to see, VAB, right? VAB. Where's VAB? I didn't name it. Okay, let's see what's the name. This one is the VAB. This is the VP4. VP4 is the VAB. VP4. And here? 0, 1. Right? Let's look at the VA small n. Inverter. This one, VA inverter. You got here? 6 step. They call it 6 steps. I'm going to plug the VAN, the grid voltage here. Let's put it right on top of this. VAN. It should be exactly in the same phase, right? You got here? Because I selected the phase the same, right? Let's plot the I. current I going to the grid. Okay, go check with the books, of Ned Mohan, the simulation, the result you have. It's going to be exactly the same. That's exactly what it is. Now let's look at the P and Q. P was a W31, right? And Q was VAR 31. Let's run the simulation full time. Is that here? How much is this one? Can you guys read this one here?
No.
25, right? Is almost zero. Look at the war, because that's the reason I'm saying. How much is the war? 4.8K. They exchange only reactive power. Somebody say this Q is zero. Q is not zero. Go think about why Q is not zero. Think about why even you write it in your report. I'm not going to say, you should display. But see, this is a Q. Now let's put it 90 degree. See, this one is a 5K. This one is a 25 watt, right? Let's go 90 degree ahead or forward or back. Let's go to the simulation. I'm going to go 90 degree ahead. Do you think P is going to go up or not?
Yeah.
Why?
Because it looks like it's inductive.
No. Anybody can tell me why? Remember last class?
The output voltage and current in phase.
I got the equation P is equal to what? Vt E over X sine delta, right? How much was the delta in the first part? How much was the delta? Zero, because they were in the same phase, right? What was the delta? The phase difference between the grid voltage and inverter output, right? It was zero, right? You got the zero power. Go look at the equation I had in the last class. It said Vt E over Xs sine delta. P and Q I derived them for you, right? Go look at those equations. If delta is zero, P is going to be zero, right? Here we have a little bit more, not exactly zero. Why? Because that equation is for first harmonics, right? But we have the other harmonics in the system, right? Examples I showed you in the class. I said it's going to be 403 watts. 400 was the first harmonic, 3 watts was the rest of harmonics, right? So this 25 we had before, it was coming from there. But now look at here. I put the delta, how much? 90. How much is it? Can you read it here? 58K, 58 kilowatt. Did I hear how much is difference? Q is something here, you can see. No, sorry, this is the P. 62 kilowatt, right? And Q is here. Minus 50. Now go make it here. And look at here, look at this one, 90 degree shift. Now the inverter is leading 90 degree, right? You need to discuss all this in your report. What does it mean? How we are acting, those kind of things. Let's go to this one, minus 90. Let's make it minus 90. Okay. Look at here, guys. How much is this number? If your eyes are like me, you cannot read it from there. This is minus 63. What happened? This is a P. Huh? The direction of power change, right? This is what they do with the charging your car at home. You inject the battery toward the battery. You inject the power toward the battery. But now they're talking about it. You can use your car as a UPS, mobile UPS. If you want 120 volt, they're going to put a plug on your machine, those electric car. You can have 120 volt output. But usually you don't do that because you want to destroy your battery for. If it's emergency, you can do that. You don't say you use it for emergency. But my point here, the direction change. But Q still is here, the same thing. You guys will discuss all this thing. Now, let's go to the sine PW. If you guys, you go through it, spend time on it, try to understand it, it's very simple and very fun. And if you're not, just look at this picture, you're not gonna understand anything. Sorry, I'm saying that, but you're not gonna get it at all. Is it this one or that? Sine PW? I think it's this one. Yes, that's the sine PW. Look at here, the only things I did, the same waveform. Let me make this one bigger. Look at here, this one is not coming. See, here what I did, now I made this one 1. Look at here, 1. Instead of being 400 AD, because this is important, I'm going to compare it with the other waveform. On the 6th step, just I was comparing with how much? 0, right? Here I'm comparing it with this waveform, this triangular waveform. This is the VTRI, 6 kilohertz, this is blah, 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 those kind of things are going to build it. Let's run this case. Let's run this case. Oh, you know what? Let's close it. Yeah, let's come back here. Now, one more thing that I want to plot. No, I did plot the current here. Look at the current here. Look at the current here. It's kind of flat top. It's not bad, but it's flat top. Now we're going to go to sine PW. Look at this current. Look at, compare this current from the 6th step to the sine PW. Now the one I'm going to plot now. Which one? We'll plot this one and go. Harmonic elimination for the next class. Okay. Let's look at this waveform. First, look at the current. See, still that current is here. You can see still that current is here. Let's look at this new current. Here. This is much better than that. Yes, there's some ripple here, right? But in the sine waveform, this is not flat top anymore, right? This is the first advantage of that. And I'm switching this 6 kilohertz. If I make this one, for example, 15 kilohertz, you're going to see perfect sine waveform. This thing's also going to go away. This ripple is going to go away. Now let's look at the V. Do I have a VAN inverter? I don't know what's the VA. Let's look at it. This is a grid voltage. So this one should be inverted. Yes, look at this here. This is the V inverter. These are in the same phase. Put them in the same phase. You got here? This is when you're chopping it. The overall waveform is like a 6th step, but there's a loss of chopping here going on, right? You can compare this current with that current to see how much it's better. Let's look at the power. Active power and reactive power. This is the second phase. This is the phase 2 of your project. W. You got here. I think I changed the value. No, this one is not stable. No, we cannot use this one. And what's that? We can also have VTRI. This is the V control. I'm going to put the VTRI right under that. VTRI. See, this is the V control. The peak is not even, I'm going to put it 1, I put it looks like 0.8, you know. MA is 0.8. This is the V control, and this is a triangular waveform. Let me plot them on top of each other. Let me get rid of this one. Screen, lid, and the last one is one we control, and VTRI. Let's look at this picture. See? This is your control waveform. This is your triangular waveform. Let's zoom in. Let's zoom in here. This is going to be sharp coming down. This is because of the simulation step time I have. You know, if you make it very small simulation step time, this one will come here, up, here, down, like that. So what this is see, control and PIR, they are crossing each other and creating solutions. So this is the phase 1 of your project. Already I gave it to you. Phase 2 is going to come very soon. As soon as we said Tuesday after next Thursday, right? So I'll tell Arnold to put the date there. I don't know what date it is. Week after that, you are going to turn in your second phase of the project. We're going to basically the same thing with the sine theta value. And 1 week after that, I'm going to give you almost the final part, which is all the controls. We're going to go over it. And there's one more phase, which is the maximum power point tracking. That one is still that one is phase 4. But so the first 3 phases is going to come very soon. You know, already have phase 1. Week after that is going to phase 2, and week after that phase 3. You know, and work on it. This is going to be 40% of your total grade. You know, so try to work on it. You know. Question?
Why do you use a triangular waveform? Would any waveform work?
Yeah, you can use tools, you can use it. They call this one up and down. They call this one up, down. If you use DSP, it could be just counting up like a star. Up, down. There is no down. Up and suddenly come down. You know? But this is the up, down. This is kind of symmetric. We like it because of that. But it could be otherwise. It could be down. You know, you're here, you count down to 0, again you jump to this. This is the way you implement DSP to generate this signal.
Also, with the sine viewing, you have I guess high frequency failure waveforms. Do you get a lot of switching losses, or?
You have as well as switching loss. You know, we are going to get lots of switching loss. Let me show you some tools for those ones still there here. Let me show you one more thing. Because you made a mistake. Let me show you this. There's another fun thing here. You don't know how good is PC. You know how much is the pain to calculate this kind of thing, but I'm going to show you something over here. I did all my PhD with PC in my dissertation. Now, it is one. FFT. All those way from the over there. The first one is the current. We got here. Almost clean. You see, this is a little harmonics here, a little bit harmonics here, right? The second one is the grid voltage. Grid voltage is a perfect sine waveform, right? There's nothing. This is the one we had. This is the inverter output. The guy here. You need to zoom in to see it here. Let me zoom in here. Because you need to do kind of harmonic analysis. The more you write, you know, you're gonna have a scale, or no, it's gonna have a scale. And it's going to put your filter in that scale and weight. You know how much weight? You're going to get weight, you know, in your report. So, see, look at here. This is the first harmonic, right? I know, this is we can go check it, see what number of harmonics. See, this is kilohertz. See here? I can tell you exactly how much is this one. See, if you come here, you can go check it with that one. This is I think this is a 5.5. This is something like a 5.75. Just go check it with that table I gave you. So it's going to be MF. This is 6 kilohertz, 60 hertz. MF is 100, right? So it's going to be 100 MF. We're going to have MF and MF plus minus 1, right? So 2 MF plus minus 1. I believe it's going to be that. So you go check them to see, make sure what it is here. But my point is, look at here, how nice is this one? How much you need time to calculate all those Fourier series? Oh, yeah. And another block here, I tell you because for those when they're going to do the report, go to elements here. There are lots of useful tools here. Let me see. There is a THD meter also. You know, if you go, I don't know where it is right now to tell you, but there is a THD block. You can put it on your program in your main body, and it calculates the THD for you. How much is the THD for the car? So how much this thing makes it easy for design and those kind of things. My intention is to teach you how to use this software more efficiently, you know, because this is very good software for power electronics modeling, simulation, design, this kind of thing. Very good software.